Okay, here's the setup. We're running on the inverter powered from the main battery. There's no external bias supply. Everything is running off of the main battery. We have oscillations. We have a negative going gate pulse. Can you see all the parameters there? Negative going gate pulse, common MOSFET drains, math trace, battery voltage, CVR voltage, or current. So the math is multiplying these two traces together, and there you go. And if you look down here, you'll see that you have negative mean, and I'm also computing the area of those lobes. So if the area is negative, that means that the bottom lobes are bigger than the top lobes. So area is negative, mean value of the math trace is negative, everything is negative. Okay, we're measuring everything at the board in the usual way. Now I have this decoupling capacitor set up here. This is about 10 microfarads. Combination of polypropylene caps and some monolithic barium titanate caps in there, a various assortment, giving about 10, slightly over 10 microfarads of capacity. It's not hooked up now, and so you can see that there's a negative mean power, right? Okay. Excuse me. Allergies. Alright, so now what I'm going to do is just hook up this decoupling capacitor there. Okay. So now, if you look, you'll see that as the time goes by, the mean value there becomes less and less negative until finally it becomes positive. And the same thing with the areas. There are momentary excursions where the mean is computed as negative, but the means is going positive now with the addition of that decoupling capacitor in there. There it was. Okay, so now I'm going to unplug the decoupling capacitor. And you see that mean value goes down and stays consistently down. All I'm doing is unplugging and plugging this capacitor to the negative pole of the battery. It's across the whole battery stack. Okay. So there's the means and the areas with the cap unplugged. I'm plugging it in now. Takes a little while for the scope, which is computing across all of the samples, to catch up with the true state of affairs, but it eventually does. And begins to show the positive means there. Okay, so the means now are strongly positive. Now I'm going to unplug the cap again, unplug it. And the means right away go negative. Okay, again I'm going to plug the cap in right now. And since it's averaging over multiple cycles, it takes a little while for the mean to change sign, but as the scope computes more and more cycles with this state, the mean approaches 0 and then changes sign and gets mostly positive and then stays strongly positive, as do the areas. Okay, now I'm going to unplug the capacitor. Okay, so the decoupling capacitors stop the negative power accumulation, and here's what it looks like on the waveform trace. So I'm just going to plug it in now. See, there's a little bit of difference. That's plugged in, that's not plugged in, that's plugged in, that's not plugged in. And that's enough of a difference to change the sign of that math waveform. Plugged in, not plugged in. Plugged in, not plugged in. Okay? So once again, we're running off of the main battery only through the charge pump inverter, which is supplying a negative bias signal to the function generator plus input through the potentiometer and the 10R dropping resistor, not using the 50R in there. All scope probe leads are grounded at the board. All probes are taken at the board. There's no need to add any wire or move the probe leads around or anything. This is all just done by the addition of decoupling caps. Now, you'd get more of an effect if you spent a little bit more time on it, I'm sure. But I think that we've shown the effect amply. So right now we're getting a mean power of negative value with the cap unplugged. Now I'm going to plug the cap in right there. And it takes a few moments for the scope to compute over a number of cycles. Until finally the mean of the mean power goes positive and stays positive. Now I'm going to unplug the capacitor. And we get that negative power value again. Focus. All right, thanks for watching.